Welcome. The topic we'll be discussing in this lecture is NUMA, Non-Uniform Memory Access. This is one type of multiprocessing system. So if you recall from the beginning, as per Flynn's what you call classification, the different multiprocessors are classified into different categories like SISD, single instruction stream, single data stream; SIMD, single instruction stream, multiple data stream; MISD, multiple instruction stream and single data stream; and MIMD, multiple instruction and multiple data stream. So if you recall, under MIMD, again we have two types. Under MIMD we have two types. What are they? We have shared memory, and also we have distributed memory. One is shared memory and the other one is distributed memory. With shared memory, we have two options. One is SMP, symmetric multiprocessors, which we have discussed. The other one is NUMA, non-uniform memory access multiprocessors. So that is what we are going to discuss in this lecture. Okay. And under distributed memory, we have clusters, which we have already discussed. Right. So this is the brief introduction, or it just shows like where we are in the course. Fine. So NUMA basically provides one alternate to SMP. It is an alternate to SMP. So before going to the actual NUMA architecture and all, first let us try to understand what is meant by NUMA. So first let us define UMA. What is uniform memory access? Uniform memory access means in a multiprocessing system there will be many processors. So different processors can access the memory in a constant time. That is called as uniform memory access. The content can be in any part of the memory, but all the processors can access different regions of the memory in the same time, and they can access the memory either by using load instruction or by using store instruction. Okay, so that is how uniform memory access is defined. So uniform memory access in the sense all processors can access all parts of memory by using either load or store instruction, and the access time for all regions of memory is same. It is not that for some region the access time is more and some region it is less. No, for all region the access time is same. Okay, access time to memory for different processors is the same, right? So for a given processor, accessing any part of the memory will be of same time, right? Similarly, if you take different processors, for different processors also accessing any part of the memory will be of same time. Okay, so if memory is something like this, processor n is here, processor n also can access this region of memory in x amount of time. Processor 1 also can access this region in x amount of time. Okay, that is what is called as uniform memory access. Different processors can access the memory in the same time, irrespective of where the content is stored in the memory. The next is non-uniform memory access. With non-uniform memory access, the memory access time will not be same for different processors. The memory access time will not be same for different processors. For different processors, the access time will differ. Here also all processors can access all parts of main memory using load and store instruction. Every processor can access every location of the main memory using load and store instruction. But access time of processors differs depending on the region of main memory being accessed. So this is with respect to a single processor. For a particular processor P1 to access the memory, for example, if the memory is placed something like this, the processor may be able to access this portion of memory relatively quickly rather than this portion of the memory. So depending on the region of the memory, the access time of the processor will vary. Similarly, different processors access different region of memory at different speeds. Okay, for example, if there is a processor, this is P2, it is placed here. For this processor, this region maybe this can access this region quickly, but it will take long time for this processor to access this region of memory. Okay, so this type of memory access is called as NUMA, non-uniform memory access. So in a uniform memory access, all processor can access all memory regions in same time, whereas in non-uniform memory access, different processors will access different regions of memory at different speed. Okay, yeah. So there is another third category which is called as CCNUMA. CC stands for catch coherent. CC stands for catch coherent NUMA. So this is also, it's a NUMA, that is it is a non-uniform memory access technique, that is different processor access the memory in different time, different speed, but it also ensures catch coherence. It also ensures catch coherence, that is it will make sure that the catch of the different processors will be consistent. Okay, so a non-consistent NUMA, incoherent, or if the catch is inconsistent, if the catch coherence is not maintained, in a normal NUMA the catch coherent will not be maintained. Okay, whereas in a CC NUMA the catch coherence will be maintained. If catch coherence is not maintained, then such an NUMA will be similar to cluster. If catch coherence is not maintained, then such an NUMA will be similar to clusters. Okay, so here in this topic we are going to discuss about catch coherent NUMA. We are going to discuss about this particular NUMA in detail. We are going to discuss about catch coherent NUMA in detail. Okay, so I think it's clear. So let me brief. So we are discussing about NUMA. Actually, it is one type of MIMD, multiple instruction, multiple data stream. In multiple instruction and multiple data stream, again we have two types. What are they? One with shared memory and the other one with distributed memory. So this comes to the one type of shared memory. So this is an alternate to SMP. There is another type of shared memory scheme. What we have is SMP, symmetric multiprocessors. Okay, so here first we should define what is NUMA. So before that we are defining UMA, uniform memory access, which means that different processors can access different regions of memory in the same time. Whereas in case of NUMA, different processors access different regions of the memory at different speeds. Okay, in catch coherent NUMA, it is an NUMA where catch coherence is maintained. It's a NUMA based multiprocessing system where catch coherence is maintained. Okay, fine. So this is the brief introduction to the terminologies that are used. Now let us see the motivation. Why should we discuss NUMA? Already we have discussed SMP and clusters. Is that is not enough? Why do we need one more type of multiprocessor which is called as NUMA? Okay, so the reason is there are some drawback with SMP and clusters. That is the main reason why we are going for NUMA. So what is the drawback with SMP? The drawback with SMP is the system bus. The system bus, because in SMP we have multiple processors. If these processors want to access the main memory, they should access via the system bus. But system bus is a slower device. So when the processor access the main memory through the system bus, the processor speed also will be reduced. To avoid that only we are introducing catch, L1 catch and L2 catch. But again, introducing L1 catch and L2 catch, it will surely reduce the access to system bus, but it provides a restriction. Introducing L1 and L2 catch, it also provides a restriction on the number of processors the system can have. It provides a restriction on the number of processors the SMP system can have. Okay, the reason is if you keep increasing the processors, if you keep increasing the processors, then what will happen? The more the processors were increased, if you keep increasing the processors, the more you increase the processor, there is a more possibility of catch miss. Okay, as processors increases, so let me call it as processor increases, what will also increase? The number of catch miss also increase. So CM is catch miss. The number of catch miss also will increase. If catch miss increases, then what will happen? System bus will be accessed more and more. If system bus is accessed more and more, then the performance will degrade. Okay, if the system bus is accessed more and more, then what will happen? Then the performance will degrade, right? So this is the drawback with SMP. So the drawback with SMP is mainly it is centering around system bus. As the system bus is slower, we are introducing L1 and L2. But when you introduce L1 and L2, there is a restriction on the number of processors that can be placed on the SMP. Because if you increase the number of processors beyond a certain limit, then as the number of processor increases, the number of memory access will increase. Then the number of cache miss will increase. So you may have to access memory more and more. Then again you have to use system bus, which will degrade the performance. Okay. So if you take a typical SMP system, it will have processors ranging from 14 to 64. So the number of processors that will be normally in a SMP system is, it will be somewhere between 14 to 64 processors. Okay. If you increase the number of processors beyond 64, if the number of processors were increased beyond 64, then its performance will degrade gradually. So this is the drawback with SMP based multiprocessing. Now coming to clusters. In clusters, we have individual systems. These systems group together, and they provide an illusion as if it is a single machine. But actually there are individual systems, and these individual system has their own private memory. These individual systems have their own private memory, and cache coherence here it is maintained at software level. It is not maintained at hardware level. Cache coherence is maintained at software level, and it is not maintained at the hardware level. And also clusters don't provide the flavor of an large scale multiprocessing system. So these are the drawback with clustering. Actually it is not, the main drawback is cache coherence is provided at the is provided at the software level, not at the hardware level, as there is only private memory with each computers. Okay. So because of these drawback, we are going for NUMA, right? Because of these drawback, we are going for NUMA because we want the flavor of a large scale system. We want the flavor of a large scale system, and we want to keep many number of processors in the large scale system, and that is the main reason why we are going for NUMA, right? So with NUMA, okay, with NUMA, what we can achieve in the sense, so there are some examples, like there is one type of processors uh, called silicon graphics origin NUMA system. Okay, the name of the system is silicon graphics NUMA system. It is silicon graphics NUMA system. Silicon, yeah, graphics NUMA system. This particular system, if you take this particular system, silicon graphics NUMA system, this is one type of NUMA multiprocessor. So this particular system can support up to 1024 MIPS or 10,000 processors. It supports this many processors, 1024. Okay, whereas if you see SMP, it can support only maximum this many processors, 14 to 64 processors. But the silicon graphics NUMA system, it supports 1024 or 10,000 processor. Okay, the type of the processor is called as or 10,000. Okay, it supports 1024 processors it can hold, right? Similarly, there is another NUMA system which is called as Sequent NUMAQ. Okay, so this system is called as Sequent. It's just the name of the system. Okay, it is called as Sequent NUMAQ, right? Sequent NUMAQ. So this system can support up to 252 Pentium 2 processors. Sequent NUMAQ. Okay, so this system can support up to 252 Pentium 2 processors. Okay, I will write as P2. So this system can hold 252 number of Pentium 2 processors, whereas the first one can hold 1024 processors. Okay, so this is the advantage that we are going to get with NUMA. You can have more number of processors than what SMP can provide, right? So this is the motivation behind NUMA. Okay, so whatever we have discussed, that was mentioned here. SMP has a practical limit on the number of processors that can be used. Okay, so the number of processors limited to 16 and 64 processors. Okay. In clusters, each node has its own private memory. Applications do not see the large global memory. There is nothing like global memory. So applications do not see the large global memory. Cache coherence is maintained at software level rather than at the hardware level. Okay, these are the drawbacks with cluster and SMP. That is the reason we are going for NUMA, because we want to retain the flavor of a large scale system. Okay, we want to retain the flavor of a large scale multiprocessing system. Okay, so the core objective of the NUMA is to maintain a transparent system with a memory while permitting multiple processor nodes, each with its own bus or internal interconnection system. Okay, so because of these drawbacks, we are going for NUMA. Now let us see the architecture or the organization of NUMA, how NUMA systems are organized. Okay. So in NUMA, the basic building block of an NUMA is a node. So this is a node. Here actually only 3 nodes were shown, but the system can have many number of nodes. So this is a node. Let us call this as node 1. This is another node. This is another node. Okay, let us call this as node 2. Another node. Okay. Similarly, this is another node. Let us call this as node 3. So the basic building block of an NUMA is a node. Okay. And if you take each node, basic building block of an NUMA is a node. Okay. And if you take uh, each node, each node can have many number of processors. See, this particular node, it has n processors. It may have 100 processors or 200 processors. Similarly, this node, you see, it can have any number of processors, 100 or 200 or whatever the number. Similarly, this node can have n processors, and each processor will have its own L1 and L2 cache. Every processor will have its L1 and L2 cache, and with each node there will be something called as directory. What is this directory? Let us discuss later. Okay, I'll explain that. But just know that each processor, each node will have a directory, and each node will have its own IO devices and its own local memory. Okay, so every node will have a set of processors. Each processor will have L1 cache, L2 cache, and every node will have set of IO devices. Every node will have its own local memory, and also every node will have something called as directory. Okay, and all these nodes will be interconnected through some network. All these nodes will be interconnected through some networks. Okay, fine. So now, see, even though there are individual memory, see the memory, every node is having its own local memory, but the applications will see one global memory. But the applications will see one global, not only applications, each processors will see it as one common global memory. So for example, all these processors will see as if there is a global memory, something like this. Processor 1 does not know that it has only this local memory. No, processor 1 views this entire memory put together as one global memory. Okay, so all these memory uh, will be viewed as a single memory by the processor. Okay, so this is one of the important feature of this. Okay, from the point of view of the processors, there is only single addressable memory. With respect to each processors, there is only single addressable memory. It is not that so many memories are there, right? Okay, so this is how it achieves transparency. Okay, here we have discussed that one of the objective of NUMA is to achieve transparency. So how it achieves transparency means, even though there are individual local memory, from the view of the processor, there is only a single addressable global memory. Okay, so cache coherence is the important concept in NUMA. How cache coherence is going to be achieved? So that is pretty important in NUMA. So we'll be discussing that in detail. Okay. So let us consider something like this. Assume that processor. Sorry. Yeah. Assume that this particular processor is trying to access one particular memory location. Okay. one particular memory location. Say that memory location is not in the cache. Say that memory location is not in the cache. Then what will happen? This processor is trying to access some memory. Say this memory is not in the cache. That location, that content is not in the cache. So there is a cache miss. Whenever there is a cache miss, this L2 cache will initiate a transfer. This L2 cache will initiate a transfer. As a result of that, the content will be checked in the main memory. Processor is not doing this. Please remember, processor is only placing the request that I want this data. If the data is not in the cache, whenever there is a cache miss, this L2 cache will initiate a transfer. As a result of this initiation, the content of main memory of the local main memory will be checked. The content of the local main memory will be checked, whether that particular content is available here or not. If it is available, it will be fetched and it will be given. Suppose whatever the processor is requesting, if it is not available in this main memory, in the local memory, then it means it is in some remote memory. It is in some other node. Now this request will be transferred to the interconnection network. Okay, this whatever the previously the request came to main memory, that will be automatically transferred. Not someone is transferring. That will be automatically transferred to the interconnection network. Now the interconnection network, it is the job of the interconnection network to identify where the data is available, in which node the data is available. It will be fetched and it will be available in the common system bus, and from common system bus it will be shared, it will be transferred to this particular node system bus, and again from this particular node, this particular node's main memory, again from this node's main memory it will go to this local bus. From this local bus it will reach the processor. Okay, but actually processor does not know all these things. Processor does not know that this data is not available. Only processor does not know that this data is not in cache, alone cache. It is not in main memory. It has been fetched from remote location. All these things will not be known to the processor, so that it is called as transparent. Processor will just place a request. It will get the content. Okay, maybe some cases with delay, some cases without delay. When it is in cache, it will get without delay. If it is in the local memory, it will get with little delay. If it is in remote memory, the delay may be more. But from where it is coming, how it is coming, all these things processor does not know. Okay, so that is what this is how the cache coherence is maintained at the top level. Okay, say when a requested memory, processor is requesting some memory, any one of the processor. Some processor is requesting some memory content, and if that content is not in the processor's cache, then what will be done? These are the steps. L2 will initiate a fetch operation. If the desired line, whatever the line the processor is asking, if that is available in the local portion of the cache, then fetch it and give it to the processor. Otherwise, an automatic request will be placed on the interconnection network. Okay, and then the desired data will be delivered to the local system bus, and from there it will go to the requesting cache. So all these operations will be automatic and transparent to the processor and the cache. Both the processors and the cache, they don't know that this request has been automatically forwarded to elsewhere and this is how the job is done. No, they don't know this. Okay, right? Now how the NUMA is doing this? How NUMA is doing this? How NUMA is achieving cache coherence? So for that what NUMA does, in the sense, for that purpose only, each node in the NUMA must maintain something called as a directory. This is the reason each node in the NUMA, so everything, this is a node, right? So every node in a NUMA should maintain something called as directory. Okay, why this directory is to be maintained? This directory is to be maintained, this directory will give an indication of the location of the various portion of the memory. This directory will give an indication of the location of the various portion of the memory. Processor does not know the various portion of the memory, but directory knows. Okay, so directory is also something like a processor. You can assume directory, it also has some processing capability. It knows the various portion of the memory. Directory, in each node's directory, this device, the directory knows like which is its local memory, and what are the other remote memories, that information directory alone knows in a given node. Okay, and also directory will maintain the details of like the cache state information, the cache status information. Okay, for example, say for example, some particular line may belong to this particular main memory, this node's main memory. Okay, say a particular line 28, it belongs to this particular node's main memory, node 1's main memory, but some other processor or some other node might have requested this line also. As a result, it may be available in this particular node also. It may be available in this particular node's one of the processor's cache. Say processor n's cache also, this line 28 may be available. So in that case, the directory will maintain, like for this node's main memory, in this particular node's main memory, which are the lines which is present in other processors cache. This detail also this directory will maintain. Okay, so to maintain cache coherence, each node will use something called as directory. So the directory provides a indication, it provides an indication of the location of the various portion of the main memory, like which is local memory, which is remote memory, all those things. Apart from that, it also contains the cache status information. It also holds the cache status information. Okay, so with this knowledge, let us try to discuss in detail how a processor accesses some memory content which is not available in the local memory, but it is available in the remote memory. Okay, say for example, now we are going to discuss a scenario. Say for example, this particular processor P1, okay, this particular processor P1, uh, or let us say some other processor. Okay, sorry. Okay, take this. Say here. Okay, say the processor P3. There is a processor somewhere here. Processor P3 from node 2. This is node 2, right? From node 2, it want to access some particular memory location. Okay, processor P3 from node 2, it want to access some memory location. Say it want to access the memory location 798. Assume that that content is not available in the cache. If it is not available in the cache, it will create a cache miss. Now L2 cache will create a L2 cache will create an request, right? It will create a fetch operation. It will create a fetch operation. As a result, the content will be checked in the local memory. Now the content is not available in the local memory. If the content is not available in the local memory, then what will happen? If the content is not available in the local memory, then actually now directory will come into picture. When the content is not available in the local memory, the directory will find out. The directory will find out that. So when the L2 cache has created a fetch operation in the main memory via the system bus, it is via the system bus, right? Or it can also be called a Snoopy bus. Via the Snoopy bus, the directory will check it, and it will understand that okay, whatever the content the processor P3 is asking, this content is not in the local memory, and also it knows that it is available in which node. So the directory knows that it is available in node 1. It is available in node 1. Now the directory will place a request to node 1. Now the directory will place a request to node 1 on behalf of the processor P3 that I need this content. Okay, this request will go to where, this request will go to the directory of node 1. This request will go to the directory of node 1. This request will go to the directory of node 1, and node 1 will again place a request that I want this content, okay, from its main memory, because that content is in its main memory 798. So node 1 will place its request. Okay, now this data will be directory 1 will place the request. Now the data will be given to directory 1 via the system bus, okay, via its own local system bus. Now the directory 1 will give this data to directory 2. This is node 2's directory. Okay. Now the directory node 1's directory will give this data to node 2's directory via the interconnection network. Now the data is reached node 2's directory. Now node 2's directory will place it in the local system bus, and then it will reach the processor 2. Okay. So this is the sequence of steps which are required for a processor to access some memory lines which are not in the local part of the memory. Okay. So that was explained here in step by step. Say the processor 3 of node 2, okay, processor 3 of node 2 is requesting the memory location 798, which is in node 1's memory. But processor 3 don't know all these things. Processor 3 of node 2, it is just placing the request via the Snoopy bus of node 2 for location 798. Okay. So the directory of node 2, node 2's directory recognizes this, and it checks, and it knows that it is not in the processor 2's memory. It is not in the processor. It is not in the node 2's memory. It is not in the node 2's memory. Rather, it is in node 1's memory. Okay. So node 2's directory is placing a request for node 1's directory. Now node 1's directory will place a request for the content. Okay. So node 1 directory is also something like a processor. So it places a request as if it was a processor. As if it were a processor, it is placing a request that I want the content. Okay. Now node 1's directory will got the content. Okay. And it will be placed in node 1's main memory. It will be placed in node 1's main memory, and from node 1's main memory it will be okay, data transferred to, yeah, so it will be placed in node 1's main memory, place data on the system bus, and data is transferred to node from first it is reaching node 1's main memory via the system bus. Okay. Once it has reached node 1's main memory, from here it is transferred to node 2. Okay. And it reaches where it reaches node 2's directory, and node 2's directory places the data in node 2's bus, and now finally it reaches the processor P3 of node 2. So this is the sequence of things which happens when a processor requests memory content, but that memory content is not in the local portion of the memory, but is in the remote portion of the memory. Okay. Now here how cache coherence is achieved. Cache coherence means what? This is just transferring the data from a processor is getting the data from the remote cache, from the remote memory to the local memory. Cache coherence means what? Now who got the data? Processor 3 of node 2 has got the data. But originally the data belonged to whom? Who is the owner of the data? Node 1 is the owner of the data. Okay. But now if processor 3 of node 2 has modified this data, then that change should take place in node 1. How it will take place? That is what is called as cache coherence. Are you getting? So far what we have discussed is how to transfer the content from one node to another node, or data from some node to different node. Okay. Now if the new node who got the data, if they have modified the data, how the change will reflect in the other processor who is having that data. So that is what is called as cache coherence. So cache coherence, how it is achieved, that we are going to discuss at a brief level, not in detail. So as a continuation of the previous example, assume that, see, now the processor 3 of node 2 has got the data, got the content of location 798. Okay. Say assume that node 2's cache line has been modified. So node 2 has got this, processor 3 of node 2 has got this data, right? Okay. So that is processor 3 of node 2, say it has modified this particular content. Previously whatever it got from node 1, it has changed it. If it has changed, it means it should inform to all others, because somebody else also may have this same data, some other processor. They may be in the same node or in different node, they may have this same data. So they should know that this is modified, so that they can invalidate it. So immediately after modifying this content, this particular processor 3 of node 2, it will send a broadcast message it will send a broadcast message via the system bus. It will send a broadcast message via the system bus that I have modified the content of the location 798. Okay. Now everybody, all the processors in various nodes, in different nodes, will receive this message. Node 1 also will receive this message. Okay. So node 1's directory knows that, okay, I am the owner of this content, but now it is actually node 1's main memory. So it reaches node 1's directory also. So node 1 knows that I am the owner of this content. Now node 2 has already modified this. Node 2's processor 3 of node 2 has modified it. So node 1 will invalidate that particular line. Location 798, it will invalidate. How long it will invalidate means until it is returned back. Okay, it should, if it is returned back, then again it will become valid. Who should write it back? Processor 3 of node 2 should write it back. Okay, until the write back is not done, it is invalid. Like that, it will mark the status for this particular line. Okay. Similarly, this broadcast message will also reach other nodes. Say if some other nodes processor also having this location 798 in their cache, then they will just invalidate that, because already processor node node 2 has already modified it. Node 2 of your processor 3 of node 2 has already modified it. So if somebody else also having this same content of location 798, they will just invalidate it, or they will purge. Purge means they will remove that from their cache, because anyway that is a no more the data is valid. Okay, right? Say after some times some other node X, it can be node 5 or node 6, some other node X, it is requesting node 1. It is requesting node 1, please give me the location content of the location 798. Because who is the owner of this content 798? Node 1 is the owner. So node X can request to node 1. So say node 1 is requesting, please provide me the content of location 798. But now node 1's directory knows that its content is already invalid. How long it will be invalid? Until a return back is done. So it, as of now, it cannot satisfy node X request, but it has to satisfy. So now what node 1 will do in the sense, node 1 will force a write back. Now node 1 will force a write back. Because of this, node 2 will perform a write back on this location 798, and the content will be updated. Once that write back is done, now the node 1 will provide this particular location content 798 to node X. Okay. So this is how cache coherence is achieved in what you call NUMA. I think it's clear. So if the processor or the node who got the data has modified it, now node 2 of processor 3 has got this data from node 1, but they have modified it. The moment they modify, they should send a broadcast message. The owner also will receive this broadcast message. Node 1 is the owner. So the owner will understand that, okay, somebody else has modified, so they will invalidate this particular line until a write back is done. This message also will be received by other nodes. If other node has also cached this particular line 798, then they will just invalidate it or they will purge it. Okay, meanwhile, if some other node X request for this same line from the owner, that is from node 1, then node 1 will force a write back, so that this content will be returned back by the node 2. Once the write back is done, then node 1 will provide this data to the requested node. So that's it about what you call NUMA. So coming to the pros and cons of NUMA, the main advantage of NUMA is it provides high level of parallelism. With performance level, it provides higher level of parallelism than SMP. Because as we have discussed, with NUMA you can have 1024 processors, 252 processors, all those things. That is not possible with SMP. With SMP maximum you can have 64 processors, not beyond that. The second advantage is the bus traffic is limited. You will not be having that much bus traffic as in SMP, symmetric multiprocessor, because we are dividing it into several nodes. Okay, and this is actually one of the disadvantage. If the number of remote access increases, If the number of remote access increases, then the performance will degrade. If okay, if many of the memory access are to the remote nodes, okay, if most of the memory access are to the remote nodes, then the performance will slowly break down. And another disadvantage is it is not uh, transparent look like an SMP. Okay, see again this word transparent. It is you have to understand with context. The English meaning of the term transparent is visible. Okay, something through which the light can pass, or it is the other side is visible. That is transparent. Okay, but here we discussed NUMA is transparent, like that we discussed, which means it is actually not transparent, which is not transparent. That is, processor does not know that request is going from local cache to remote cache to the remote memory, local memory to remote memory. All these things processor does not know. That way also we use the term transparent. Okay, right? So that the usage is changing with context, so that you should understand. Here again it is said that it is not having transparent look like SMP. That is, SMP is uh, okay. So this is actually uh, what to say. This is actually the English term transparent. SMP is transparent because SMP you do everything explicitly. If it is not in, because there is only one shared memory and everything happens explicitly. But here in NUMA things does not happen explicitly. There are certain things which happens transparently. Transparently means it is hidden. In that context, processor does not know what is happening. Okay, so that is the advantage and also disadvantage, because processor did not bother. In that sense it is an advantage, but not every detail is known. In that sense it is a disadvantage. Okay, and if you want to and another disadvantage is if you want to convert an SMP system to a CC NUMA system. If you want to convert an SMP system to a CC NUMA system, then software changes are required. You cannot convert directly, because the way in which the NUMA works is different from the way in which SMP works. Because uh, because SMP NUMA requires some degree of transparency, uh, or we'll say hidden. Something should be hidden with respect to processor. Processor does not know, should not be knowing every details. So that is required in NUMA. Okay. So these are the advantage and disadvantage of NUMA. So that's it about NUMA. Okay, let us stop here. Thank you.